Hi there, this is Aditya, and today we would be talking about this mobile phone and its battery. Now, have you ever wondered what this mobile battery is made up of? Have you ever given it a thought? Most probably not, but it may come to your notice or in your attention when you see these things getting explode in news channels and all. Have you ever wondered why does these? How can they explode? These are batteries. And what is the science behind these batteries? How can these batteries power our cell phones, which is our daily drive during these days? Let's find out. Let's explore. Jumping inside a battery, we see four major parts: the electrodes, that is the anode and the cathode, the separator, and the electrolyte. Now, in the case of a mobile phone battery, the cathode is made up of lithium, but in general, for any battery, the properties and the electric potential of these materials of electrodes differ. So the question occurs, how do scientists measure the potential or the work done by these batteries in general? Now let's start by understanding what is a reference electrode. It's very clear to us that for a measurement of potential, we need two electrodes. These two electrodes are generally known as the indicator electrode and the reference electrode. For the measured potential to have a meaning here, the reference electrode must be constructed in such a way such that its composition is fixed and the response is constant over time, so that the observed changes in the measured potential is solely due to the change in the concentration of the specimen. We are familiar with the tables of standard reduction potentials, or E naught, which helps us in predicting the ease at which half cell reactions occur with respect to the other half reactions. These values of E naught are most often reported as the potential measured in an electrochemical cell, for which the standard hydrogen electrode is used as a reference. The standard hydrogen electrode is composed by an inert element like platinum, on which hydrogen gas gets adsorbed, which is immersed in a solution containing hydrogen ions at a unit activity. The half reaction of standard hydrogen electrode is given by this. It is seen that the practical use of standard hydrogen electrode is limited because of the difficulties in preparing and maintaining the electrode, basically because of the requirement of the hydrogen gas in the half cell. So nowadays, people have switched to secondary reference electrodes, for which Mohit would be continuing further.
Thank you, Aditya. Hello, everyone. My name is Mohit Raj, and I am part of group number 7 of EC project. And our topic is reference electrode. And I will be telling you about calomel electrode, also called as standard reference electrode. So, this is my whiteboard, which I recently purchased for this project, and I just wrote everything down with my marker, and I just casting it live so I can explain it even better. So, let's start. So the construction of calomel electrode is pretty simple. This is a glass tube in which in the lowermost part is the mercury, which is in the liquid form, and in the middle part is the paste of mercurous chloride and pure mercury. So this mercurous chloride is a dimeric structure, HgCl and Cl. So this Hg is in +1 oxidation state and Cl is -1 oxidation state. That's why it is called as mercurous chloride. Had it been in +2 oxidation state, mercury, then it would had been called mercuric chloride, which is HgCl2. So let's move forward. Here it is KCl. KCl acts as a salt bridge. It can also act as a salt bridge. It can give Cl minus to the solution, and this is the platinum wire. This is the platinum wire and it is used because it is inert. It does not react with the solution and does not like interfere with the reaction. So so the cell representation, if you ask me, it's pretty simple. He connected with HgCl2, He2Cl2 connected with KCl. So it's pretty simple. So now let's connect this. So how do we measure? That's the main part. So now let's connect this with a key and connect this to a solution of, let's suppose, copper. So Cu and in a solution of CuSO4. So as it's copper, so it's a reducing solution. So in this calomel electrode, oxidation will happen. Oxidation of happen means loss of electrons. So now who will lose electron? Will K plus here lose electron? Of course not. Cl minus, no, it's a reducing property. Hg plus, no, it's in already in stable state. So who will lose? So this Hg will lose. This Hg will lose electron, move to become Hg plus, and the Cl minus, that is a spectator ion, combines with this and forms Hg2Cl2 plus 2 electrons. This is the way to show this reaction. 2Hg gives 2Hg plus 2 electron minus, or if you want to show the spectator ions, that is Cl minus, we can show it like this. So now for a moment let's disconnect it, and now let's connect it with a solution which is oxidizing in nature. So in this calomel electrode, reduction will happen. Reduction will happen means gain of electrons. So here electron from here will come, gain of electron. So now who will gain electron? K plus? No. Cl minus? Of course not. Hg plus or Hg. So this Hg plus will gain electron to become stable. So this 2Hg plus gains 2 electrons to becomes 2Hg, or we can again write it in the other way with the help of the spectator ions like this one. So as there is no space, there was no space, so I wrote this again. So let's now start thinking. Yes, so this is Nernst equation. Nernst equation used to carry out the potential, calculate the potential. For the oxidation, it's E cell is equal to E naught cell minus 2.303 R upon NF log product upon reaction. So here the product is in solid state, so 1, and this Cl minus is in uh, reaction state, so Cl. And basically same thing happens in reduction. This 2G and 2 Cl minus, so Cl minus in this product, and this is in again solid state, so 1. So now these are the values which I calculated, and I just wrote upon my whiteboard. This KCl saturated comes the value of 0.242V, 1N comes the value of 0.268V, and zero point 0.1 nano it is a normal KCl. If we take, it's 0.338V. So this is the overall reaction. So now the main question is, why do we prefer calomel electrode over hydrogen electrode? Because this calomel electrode is very portable. You see, you can keep it in pocket and keep it in pocket. So it's very portable as compared to the hydrogen one, in which we have to arrange for big cylinders of hydrogen and HCl gas. In there are so many necessities for that, but this is relatively easier and portable. And also the only disadvantage of this is that it has mercury, and this mercury is a possible carcinogenic. So you need to take necessary precaution that it does not leak out if it breaks. So we will continue this topic, and I will now hand over to my fellow teammates Abhinav and Akash for the further.
Hi there. Here are a number of batteries for you, with their potential, their sizes, their powers, and whatnot. But what good are they? I mean, these terms, the potential, the power, the size of the batteries. Let's talk about them. Let's talk about the size. What good is the size? I mean, why should we even consider the size of the battery? We'll talk about that in a moment. I'll tell you why we are considering the size of the battery with the help of a practical example.
Right now, I'll be showing you a real life example where, just due to the size of cell, the Tesla company overshined Nissan in terms of battery technology. So, here it is. The Nissan battery Leaf has a huge battery cooling issue due to the big size of its cells and the absence of an active cooling method. The small multiple cell system has a big advantage, which is during high power demand situation, the discharge strain is divided equally among the cells. But if instead of this, if we had used a big cell, a big giant cell, it would have been put under a lot of strain and eventually would have suffered a premature death.
Those chemical reactions which we used to learn, and they used to mess up with our heads. Were they even worth our while? Were they worth learning? Well, some of them were. In the way when they will answer our questions like, how do we determine the potential difference? And what good is 3000 mAh in real life? The answers to this question is involved in the maths with those chemical reactions. One electron involves 1.6 into 10 power minus 19 coulombs. Now let's consider a reaction just right now, which is on your screen, this interaction involves movement of two electrons. But charge on two electrons is quite insignificant. Consider a battery in which not just two, not 200, not 2000, but more than billion electrons are moving, which is usually the case. But consider a case where the movement of electrons is in the order of Avogadro number.
So here's a little math for you guys. Order of electrons in Avogadro numbers, so 10 power 23 electrons, which equal this much in charge. Now 1 coulombs is 1 amp second, so it equals 1.6 into 10 power 4 amp seconds. Now in hours, it will be 160 by 3600 ampere hour, which is approximately equal to 4500 mAh. So what does that mean? And battery with Avogadro number of electrons flowing will give you this much of charge flow in an hour.
There's another feature in batteries which is rather a disadvantage, which is not desired but it nonetheless does occur due to one or another reasons, and which is often fatal. You might guess what I'm thinking about, what I'm talking about. Yeah, explosions. Battery exploded. What went wrong? Until now, everything was alright, electrons moving, work done. Where on earth these minuscule batteries led to an explosion? Well, to understand that, take a look at this animation.
If the internal temperature of the cell rises due to any abnormal condition, the liquid electrolyte in between will dry up and there will be a short circuit between anode and cathode. This will lead to an explosion.
This explosion might raise concerns. What if this happened with my mobile? What if my battery exploded? How to prevent it? Well, these things have already been taken care of. You don't have to worry about it. And more about this, you will be getting from my buddy, Akash Roy. So hang in there.
Hi, I am going to talk about quality management of battery production. So, here is a lithium ion cell. It is primarily used in mobile phones, in electric vehicles, etc. So, how does the industry make sure that the battery does not explode? In other words, what are the quality control tests that are done in the industries? Well, let's discuss that in the video. Here are some prismatic lithium-ion cells. Now let's discuss the quality control tests that are done in the industries. The process chain shows the methods and tests the batteries go through. Let's discuss some of the terms. High pot test, also known as the high potential test or the high voltage test. Here, a bunch of cables is first connected to 0 volt. Then they are connected to some AC source. If a large amount of current flows through the cable, then it fails the test. Second, leakage test. So, why do you think leakage occurs in a battery? Well, leakage happens due to unused batteries which are kept in devices for too long. For leakage test, voltmeter on a low setting should be used. Let's discuss about some of the statistics that are employed for the study of quality parameters of a battery. By quality parameters, I mean battery capacity and battery weight. For battery capacity, a one-sided Harrington function can be used. In the function, we see that the quality parameter gets better with increasing value. In battery capacity, a Deringer graph can be plotted. We see that the target value achieves its maximum, which corresponds to a desirability of 1.
Well, they say lemons can produce electricity. I am here with a lemon tree to find it out. Roll the lemon across a bed to break up all the juice packets inside and make it nice and juicy. Now on one side, stick a zinc nail and on the other side, stick a copper wire. Now you probably would not be surprised when I connect the voltmeter with the copper and the zinc and we see an electric current. Well, now if I ask you, why are electrons flowing from one metal to another? Most probably you will say because it's because of the lemon. Lemon is producing the electricity. But that's wrong. Let's get it right. Well, the electrochemical cells, also known as the battery, mainly requires three things: two electrodes and an electrolyte, where one of the electrodes must have a stronger desire for electrons than the other one, which is scientifically said to have a higher electronegativity. In the lemon battery we have copper and zinc. Copper likes having electron more than zinc, thus copper is the cathode here. But if that is the case, why don't we just hook up the copper with the zinc and let the electrons flow? And what is the need of this lemon? Well, the electrons are not just going to abandon their sweet stable little home and make the metal positively charged from one side and negatively charged from other. There are a lot of factors playing that would avoid this from happening. Well, if the zinc is losing an electron, it also has to lose protons. But how will protons, which are 1,000 times bigger than electrons, follow through wires? Well, in that case, the third component comes to play. That is the electrolyte. The wire that connects the copper and the zinc allows the electron to go easily, but protons are used compared to electrons, so they cannot move through the wire. Well, these ions or protons can move through an ionic solution. For example, a dilute solution of citric acid. Where is that found? In the lemon. The zinc is exposed to the acid in the lemon, which results in oxidation of zinc, and thus the resulting positively charged zinc ions move through the solution, while the resulting negatively charged electrons are collected at the metal and pass through the wires towards copper. Now these electrons in the copper pull out the protons from the acid or the H plus ions from the acid and they reduce him, that is, they add the electron in. The result of this is hydrogen gas. Now if we are in there, we can see tiny bubbles coming up from the copper electrode. So in summary, the electricity is not at all coming from the lemon, but it is coming due to the difference in the electronegativities of the two metals and the oxidation and the reaction happening between them. Well, you may ask the proof. What is the proof of this? Well, you most probably would have seen some YouTube videos or experiments with a lot of lemons. They connect a lot of lemons in series to get more power. But the truth is that is not necessary. By putting 3 nails and 3 copper wires in the same lemon, you can get roughly 3 times as much as the electric current, as long there is enough lemon juice in the lemon. So, the conclusion, the power is in the zinc, not the lemon. I would like to thank Karthik sir for giving us this opportunity to have fun and learn at the same time. Thank you guys for watching.